particle physics framework. Envision the universe as an expansive Lego set where everything, planets, stars, humans, and even the air, is crafted from tiny building blocks, each possessing distinct properties. The standard model of particle physics serves as the guidebook for these blocks, outlining the essential components that form everything in existence, along with the forces that bind them. However, the path to discovering this manual wasn't a smooth one. It arose from decades of groundbreaking experiments, visionary theories, and a continuous pursuit to unravel nature's most fundamental language. The revelation of the Standard Model wasn't a single event nor the work of a solitary scientist. It started in the late 19th and early 20th centuries when physicists began to probe the minutiae of matter. In 1897, J.J. Thomson's identification of the electron revealed that atoms, once thought indivisible, actually contained even smaller elements. Then, in 1911, Ernest Rutherford's gold foil experiment uncovered the atomic nucleus, a dense core surrounded by electrons. These revelations ignited a wave of research, leading to the realization that atoms weren't fundamental after all. They were made up of even tinier particles. Throughout the early 20th century, scientists discovered numerous elusive particles, and by the 1930s, the proton and neutron were recognized as the fundamental units of atomic nuclei. Yet, these findings led to more questions. Were protons and neutrons elementary, or did they also consist of smaller constituents? What forces held them together? As physics advanced, quantum mechanics and special relativity laid the groundwork for understanding particles at incredibly small scales and high speeds. During the 1950s and 1960s, the advent of particle accelerators, massive machines capable of colliding particles at tremendous speeds, enabled scientists to observe phenomena previously unseen. Every collision seemed to unearth new particles, from pions to muons to strange quarks. The influx of new discoveries was so overwhelming that physicists humorously dubbed it a particle zoo. Amid this explosion of particles, scientists began searching for a unified theory to organize these discoveries and explain their interactions. This pursuit led to the formulation of the Standard Model, a theoretical structure that combines three of nature's four fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. A pivotal idea within the Standard Model came from Murray Gell-Mann in 1964, who introduced the concept of quarks. Quarks are elementary particles that combine to form protons, neutrons, and other particles known as hadrons. Just as letters in an alphabet can form various words, quarks combine in different arrangements to create the particles we observe in nature. Initially, Gell-Mann proposed three types of quarks: up, down, and strange, which accounted for many of the particles physicists had observed. With the introduction of quarks, the notion of a fundamental building block was revived. However, there was more to uncover. The Standard Model recognizes 6 types of quarks: up, down, charm, strange, top, and bottom. These quarks join together in various combinations to form protons, neutrons, and other particles. Quarks are held together by the strong force, mediated by particles known as gluons, which serve as the glue-binding quarks inside protons and neutrons. The Standard Model also details how particles interact through fundamental forces. In addition to quarks, it includes leptons, such as the familiar electron, and force-carrying particles called bosons. Each force has a corresponding boson that transmits it. For instance, photons carry the electromagnetic force, enabling interactions between charged particles. The W and Z bosons are responsible for the weak nuclear force, which governs processes like radioactive decay, while gluons mediate the strong force that binds quarks in atomic nuclei. These discoveries gradually coalesced into the Standard Model, but one crucial element was still missing: mass. Although the Standard Model successfully explained the fundamental particles and their interactions, scientists were puzzled by how particles gained mass. In 1964, physicists Peter Higgs and others proposed the existence of a field now known as the Higgs field, which permeates all of space. Particles interacting with this field would acquire mass, much like a ball rolling through water slows down more than one moving through air. The Higgs field's existence implied the presence of a new particle, the Higgs boson. For decades, the Higgs boson remained theoretical. It had to exist according to the Standard Model, but no one had observed it. In 2012, the Large Hadron Collider LHC in Switzerland provided enough energy to detect the Higgs boson, confirming a key prediction of the Standard Model. To grasp the Standard Model, imagine an enormous invisible web linking everything in the universe. This web consists of particles that interact with one another through exchanges of invisible messenger particles. For example, if you and a friend toss a ball back and forth, the ball could symbolize a force such as the electromagnetic force. By throwing the ball, you interact with one another. Similarly, the Standard Model explains how particles exchange messenger particles like photons or gluons to experience forces. Another analogy is to think of quarks as different flavors or types of building blocks. Just as a sandwich can be made from various ingredients, particles like protons and neutrons are constructed from different combinations of quarks held together by gluons. This combination of quarks, gluons, and force carriers forms the foundation of everything around us. The Standard Model has proven exceptionally successful in describing nearly every known particle interaction and in making predictions that have withstood experimental scrutiny. However, it is not a complete theory. The Standard Model does not account for gravity, nor does it explain dark matter and dark energy, mysterious components that constitute most of the universe's mass and energy. Additionally, questions remain, such as why there are precisely 6 quarks and 6 leptons, or why particles have the masses they do. The Standard Model of particle physics is a monumental achievement in modern science, encapsulating our understanding of the universe's fundamental particles and forces. It provides the blueprint for the microscopic world, encompassing everything from the tiniest quarks to the interactions that shape the cosmos. While it resolves many questions, it leaves the door open for deeper mysteries, motivating physicists to continue exploring, discovering, and refining our understanding of what the universe is made of and how everything fits together. Superconductivity and superfluidity, the quantum revolution. In the early 20th century, as scientists began conducting experiments near absolute zero, the coldest temperature possible at -273.15 degrees Celsius or 0 Kelvin, they encountered peculiar and surprising properties in materials that defied traditional physics. Among the most captivating phenomena were superconductivity and superfluidity. These effects, which manifest in specific materials at extraordinarily low temperatures, opened a whole new chapter in physics, leading to significant breakthroughs in both science and technology. The journey into superconductivity began in 1911 with Dutch physicist Heike Kamerlingh Onnes at the University of Leiden. Onnes was a pioneer in cryogenics, specializing in achieving ultra-low temperatures. In 1908, he made history by becoming the first person to liquefy helium, reaching temperatures just above absolute zero. This achievement enabled him to explore the behavior of materials under these extreme cold conditions. One of his key experiments involved mercury, a metal known for its good electrical conductivity at room temperature. However, when cooled near absolute zero, something extraordinary occurred. At a temperature of 4.2 Kelvin (-268.95 degrees Celsius, mercury's electrical resistance, typically the cause of energy loss as heat, suddenly dropped to zero. In essence, mercury allowed electrical current to flow without any resistance whatsoever. This was the first documented observation of superconductivity. To appreciate the significance of this discovery, think of it like this. In normal conditions, when electricity travels through a wire, some energy is inevitably lost as heat due to resistance. It's similar to water flowing through a pipe, where friction with the walls of the pipe causes the water to lose energy. But in superconductors, electricity flows through the material without any resistance, akin to a frictionless pipe, allowing an electric current to potentially flow indefinitely without losing energy. This property opens up enormous possibilities for energy-efficient power grids, MRI machines, particle accelerators, and even maglev trains. But what exactly causes this bizarre phenomenon? It wasn't until 1957 that American physicists John Bardeen, Leon Cooper, and Robert Schrieffer proposed the BCS theory to explain superconductivity. They suggested that at ultra-low temperatures, electrons in a superconductor pair up to form Cooper pairs. These pairs of electrons move together in a coordinated manner, flowing through the material without scattering, which means there's no energy loss due to resistance. The formation of these pairs and their smooth movement through the atomic structure allows for the frictionless flow of electricity. Superfluidity, a phenomenon discovered a couple of decades later, shares similarities with superconductivity but occurs in liquids instead of solids. In the 1930s, Soviet physicist Pyotr Kapitsa and American physicists John Allen and Don Messiner observed a remarkable behavior in liquid helium when cooled to 2.17 Kelvin. Below this temperature, the liquid helium transitioned into a state with zero viscosity, meaning it could flow without any resistance at all. Kapitsa coined this phenomenon superfluidity. Superfluidity was later understood through the principles of quantum mechanics, specifically the concept of Bose-Einstein condensation. In simple terms, when helium atoms are cooled to extremely low temperatures, they behave more like waves than particles. These atoms overlap and move in perfect harmony, essentially forming a single quantum state. This collective behavior enables the helium to flow without losing energy due to viscosity. While superfluidity remains more confined to theoretical and experimental realms, it has already contributed significantly to our understanding of quantum mechanics and the behavior of matter under extreme conditions. The study of superfluid helium, in particular, has provided valuable insights into quantum turbulence and inspired further exploration of other exotic states of matter, such as Bose-Einstein condensates and ultra-cold atomic gases. To understand these phenomena through an analogy, think of a regular liquid as a group of people moving through a crowded hallway. Each person adjusts their pace to avoid bumping into others, leading to slow and chaotic movement. But in a superfluid, it's as if all the people were synchronized perfectly, moving in harmony without any collisions, as though they were a single entity. This is similar to how atoms behave in a superfluid state, moving collectively without friction. Similarly, imagine electrons in a normal conductor as cars on a busy road, where each car is occasionally slowed down by bumps and turns, representing resistance. In a superconductor, however, the car's electrons move in pairs, so perfectly coordinated that they encounter no obstacles, allowing them to move endlessly without losing speed. The discoveries of superconductivity and superfluidity opened a window into the fascinating, quantum-dominated world of ultra-cold physics, challenging our intuitions and broadening our understanding of matter. These phenomena not only reveal the strange behaviors that emerge at extremely low temperatures, but also offer valuable applications in technology and fundamental science. As researchers continue to experiment with these states, such as the quest to achieve superconductivity at higher temperatures, the possibilities for energy efficiency, medical technology, and our understanding of the quantum world continue to grow, promising even more groundbreaking advancements. The essence of string theory. String theory stands as a potential bridge between quantum mechanics and general relativity, two of the most pivotal yet fundamentally distinct frameworks in modern physics. At its core, string theory proposes that the universe's most fundamental components aren't particles like electrons or quarks, but rather minuscule, vibrating strings. Each of these strings vibrates at a particular frequency, and its mode of vibration determines the properties of the particle it manifests. In essence, the universe can be likened to an orchestra where various instruments produce unique notes to create the complex melody of reality. In 1970, Leonard Susskind, Holger Beck-Nielsen, and Yoichiro Nambu realized that Veneziano's mathematical expression could be visualized as a one-dimensional, vibrating string. This discovery marked a paradigm shift. Instead of viewing particles as dimensionless points, they began to be seen as tiny loops or segments of strings that could vibrate in a variety of ways. These vibrations gave rise to different particles, much like how a guitar string can produce various notes depending on how it is plucked or tuned. As physicists delved deeper into the implications of string theory, they discovered it offered a unique and extraordinary perspective, with the potential to unify all fundamental forces into a single framework. However, early iterations of string theory came with their own set of limitations and inconsistencies. For example, they predicted not 3, but 10 dimensions of space-time, 6 more than we directly experience. Initially, this seemed absurd. However, physicists soon realized that these extra dimensions might be compactified or curled up so tightly that we wouldn't perceive them in our everyday reality. As the theory evolved, physicists sought to refine it further, leading to the development of superstring theory in the 1980s. This new version introduced the concept of supersymmetry, a proposed symmetry between particles that carry forces, such as photons, and those that make up matter, like electrons. Supersymmetry added stability to the equations, allowing for more consistent models. Superstring theory proved to be both powerful and elegant, uniting all 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, under a single, all-encompassing framework. For the first time, string theory appeared to be a viable candidate for the long-sought theory of everything. In the mid-1980s, however, string theorists faced a new dilemma. Rather than uncovering a single unified theory, they found themselves with 5 competing versions of string theory, each possessing distinct mathematical structures. This was frustrating, as physicists were seeking one cohesive explanation for everything. Yet, in the 1990s, Edward Witten, a leading theoretical physicist, proposed a groundbreaking idea. These 5 theories might, in fact, be different expressions of a single, more fundamental theory. He dubbed this the M-theory, which introduced an additional spatial dimension, bringing the total number to 11. Under M-theory, strings were no longer the sole fundamental objects. Multi-dimensional branes, short for membranes, existed in different dimensions. The idea of branes opened up new avenues for understanding the universe, with one of the most intriguing possibilities suggesting that our universe could itself be a 3-dimensional brane floating within a higher dimensional space. This concept led to groundbreaking discussions about the multiverse, the idea that parallel universes could coexist alongside our own. Despite its mathematical elegance and conceptual beauty, string theory remains largely theoretical. It has yet to produce testable predictions that can be directly verified in experiments. This lack of empirical evidence is one of the primary criticisms leveled against string theory. Some physicists argue that a theory incapable of being tested may lie beyond the bounds of traditional science. However, proponents of string theory emphasize its significant contributions to understanding black holes, entropy, and even the early moments of the Big Bang. While string theory faces challenges, it continues to be one of the leading contenders for a theory of everything, guiding physicists toward new mathematical tools and ideas. It has inspired thousands of researchers and has even influenced fields outside of physics such as pure mathematics. String theory represents humanity's relentless quest to understand the cosmos at the deepest level, pushing the limits of our knowledge about space, time, and matter. It proposes that the very fabric of reality may be woven from tiny, vibrating strings. Although we may be far from confirming its predictions, string theory serves as a beacon in our ongoing search for the ultimate nature of the universe. Much like the early explorers who charted uncharted territories, string theorists venture into the abstract landscapes of mathematics and physics, driven by the hope that one day we may achieve a comprehensive understanding of reality itself. Mysteries of dark matter and dark energy. The discovery of dark matter and dark energy stands as one of the most fascinating and puzzling enigmas in contemporary physics. These two unseen entities are thought to make up roughly 95% of the cosmos, yet they evade direct detection. Their existence was proposed not because we could observe them, but due to the unusual and unexpected ways they impact the visible universe. The journey to uncover them is a winding path marked by curiosity, mathematical challenges, and the relentless pursuit of scientists who notice discrepancies in the universe that couldn't be explained. The hunt for dark matter began with an unusual observation in the 1930s by Swiss astronomer Fritz Zwicky. While studying the Coma cluster, a group of galaxies bound together by gravity, Zwicky noticed something strange. The galaxies were moving much faster than expected based on their visible mass. According to Newton's laws of motion, they should have scattered apart at such speeds, but they remained gravitationally bound. Zwicky proposed that an invisible form of mass must be holding these galaxies together. He coined the term dunkle materie, or dark matter, to describe this unseen mass that seemed to provide the gravitational force keeping galaxies intact. Although Zwicky's theory was ahead of its time and largely overlooked, the concept of missing mass reappeared in the 1970s due to the pioneering work of American astronomer Vera Rubin. Much to their surprise, the results showed the opposite of what they anticipated. Instead of slowing down, the universe's expansion was accelerating. It was as if some invisible force was pushing galaxies apart, driving the expansion of space itself at an ever-increasing rate. This unseen force was named dark energy, a mysterious pressure opposing gravity on a grand scale and responsible for pushing galaxies further and further away from each other. To illustrate this concept, imagine watching a play in a theater. The actors, lights, and props represent the visible matter we can observe, stars, galaxies, and everything we see in the universe. However, for the performance to run smoothly, there must be a team of stagehands, lighting coordinators, and directors working behind the scenes, influencing the production without being seen. Dark matter is akin to the backstage crew. It moves the scenery, sets the stage, and ensures everything stays together. Dark energy, on the other hand, is like a mysterious director making decisions that alter the pacing of the performance. It creates a dynamic force that shapes everything on the stage. In this analogy, dark matter binds galaxies and clusters together, while dark energy accelerates the expansion of the cosmic stage itself, pushing galaxies farther apart, as if continuously creating more space. Today, dark matter and dark energy remain two of the greatest scientific mysteries. Dark matter interacts mainly through gravity, forming the invisible scaffolding upon which galaxies and clusters are built. Despite decades of experiments, from deep underground particle detectors to high-energy collisions in the Large Hadron Collider, scientists have yet to directly detect dark matter particles. Current theories suggest it could consist of exotic particles, such as weakly interacting massive particles WIMPs or actions, but without direct evidence, its true nature remains speculative. Dark energy is even more elusive. While its nature is still not fully understood, one hypothesis connects it to the cosmological constant, something Albert Einstein originally proposed in his equations of general relativity. Ironically, Einstein had introduced the cosmological constant to maintain a static universe, but later discarded it, calling it his biggest blunder when he learned that the universe was expanding. In a curious twist of fate, this cosmological constant has returned as a candidate explanation for dark energy. Understanding dark matter and dark energy is critical, as they influence everything from the shape and destiny of the universe to galaxy formation and the distribution of cosmic structures. Dark matter explains why galaxies group in particular ways, while dark energy offers insights into the ultimate fate of the universe. Will the universe continue to expand forever, ripping galaxies apart in a big rip, or will expansion eventually halt? These questions depend largely on dark energy, which remains one of the most tantalizing unknowns in cosmology. Research into dark matter and dark energy continues, driven by ever-advancing technology. Telescopes like the James Webb Space Telescope and large surveys like the Dark Energy Survey are gathering crucial data to solve these cosmic puzzles. These tools allow scientists to map the universe's structure with greater precision, looking for patterns and gravitational effects that might reveal dark matter's presence or offer clues about dark energy's behavior. Ultimately, dark matter and dark energy highlight how much remains to be discovered in the universe. They point to gaps in our knowledge and urge scientists to explore, question, and push the limits of what we know. Though invisible to us, their effects shape everything in the cosmos, connecting galaxies, influencing the structure of the universe, and driving its expansion. The search to understand these forces lies at the heart of modern physics as we continue to uncover the hidden and powerful forces that shape the universe. Why the universe seems built for us. Exploring the anthropic concept. The anthropic concept is a philosophical and scientific approach that tackles one of humanity's deepest and most puzzling inquiries. Why does the cosmos seem precisely designed to support life? The word anthropic originates from the Greek word for human, and this idea essentially inquires why our universe exhibits the exact physical properties necessary for conscious beings to come into existence and observe it. This idea was refined and developed during the second half of the 1900s, gaining prominence in both theoretical physics and philosophical discourse. It has shaped conversations on cosmology, quantum physics, and even the possibility of other universes beyond our own. The narrative begins in the early 1900s when scientists started identifying the fundamental constants and forces shaping reality, such as the speed at which light travels, the pull of gravity, and the electric charge of the electron. Researchers observed that if any of these constants were slightly different, the universe would be inhospitable. Stars wouldn't ignite, atoms wouldn't bond, and life as we know it could never have formed. This observation led to an astonishing insight. The cosmos appears to be incredibly well calibrated for life to emerge, almost like a grand cosmic orchestra where every instrument is tuned perfectly to create harmony. In the 1960s and 70s, scientists including British cosmologist Brandon Carter began to clearly articulate what would later be termed the anthropic concept. Carter introduced the idea formally in 1973 during an academic event honoring the 500th anniversary of astronomer Nicolaus Copernicus. Carter posited that the universe's conditions aren't random. Instead, they seem life-favoring, optimized to support observers. This concept is generally discussed in two versions: the weak anthropic concept WAC and the strong anthropic concept SAC. 1. Weak anthropic concept WAC. This interpretation simply suggests that the universe must contain properties compatible with life because observers exist within it. In simpler terms, the reason we notice a life-permitting universe is because, had it not supported life, no one would be around to notice anything. It's a self-reinforcing idea, a tautology. It doesn't aim to clarify why the universe holds these features. It only points out that such conditions must exist for us to ask the question in the first place. 2. Strong anthropic concept SAC. The stronger formulation goes further. It proposes that the cosmos is not just accidentally fit for life, but that it necessarily brings about observers. In this view, the conditions of the universe are not coincidental. They are either required or intended to lead to consciousness. A cake in the oven. A metaphor. You might then wonder, Why does this cake have the exact elements needed to succeed? The anthropic concept would respond, the cake must have had those elements, otherwise there would be no cake to observe. Likewise, our universe is composed of just the right components for conscious observers to exist. The real question is, why does it have those specific ingredients at all? Enter the multiverse, a cosmic lottery. In the late 20th century, the anthropic concept gained even more attention as physicists proposed the multiverse hypothesis. According to this idea, there might be a vast, possibly infinite, collection of universes, each governed by its own unique physical rules and constants. In such a scenario, the anthropic concept can be interpreted probabilistically. Out of countless possible universes, we happen to exist in the one where the settings allow life to emerge, just by chance. The anthropic concept has also been crucial in shaping modern theories like string theory and certain interpretations of quantum mechanics. For example, some quantum theories propose that a system only settles into a defined state once it's observed. This viewpoint aligns with the anthropic idea, suggesting that observation plays an active role in defining the properties of the universe itself. The ongoing debate, however, not everyone agrees on its value. Some researchers and thinkers claim that the anthropic concept lacks scientific rigor because it doesn't yield testable predictions. They argue that it feels more like a philosophical dodge than a genuine explanation, offering an easy way out of deeper scientific inquiry. Nonetheless, other scientists defend it as a crucial part of cosmological reasoning. To them, it keeps researchers from chasing unnecessary explanations for features that are simply prerequisites for us to be here. For instance, rather than investigating why gravity has a particular strength, one might simply conclude, if it didn't, we wouldn't exist to question it. Contemporary insights and applications. More recently, the anthropic concept continues to influence groundbreaking ideas. Physicist Leonard Susskind, a leading advocate of multiverse theory, suggested that the anthropic idea might help resolve the cosmological constant puzzle, the mystery of why this constant, which governs the universe's expansion rate, has such a precise value that enables galaxies, and thus life, to form. Another significant figure, British physicist Stephen Hawking, found the concept both intriguing and problematic. While he acknowledged its usefulness in explaining why life is possible, he remained skeptical about attributing any deeper purpose or intention to the universe. Instead, Hawking preferred models rooted in mathematics and empirical science. Final thoughts. The anthropic concept remains one of the most fascinating and divisive ideas in today's scientific landscape. By concentrating on the requirements for life, it pushes us to rethink our understanding of the universe. It encourages reflection on whether these life-permitting conditions are purely coincidental or part of a larger framework. Whether seen as a circular truth, a guiding lens, or a suggestion of cosmic purpose, the anthropic idea challenges us to consider our unique position in the vast expanse of existence. The universe, with its finely tuned balance of laws and forces, is both astonishingly intelligible and deeply enigmatic. Maybe, just maybe, it's calibrated so that we could question it in the first place. The surprising glow of black holes. Unveiling Hawking radiation. Colossal cosmic entities capable of consuming anything that ventures too near, even light itself. For generations, they were believed to be ultimate celestial prisons. Once anything crossed into a black hole, it was considered irretrievably lost. But during the early 1970s, a brilliant young theoretical physicist named Stephen Hawking disrupted this long-standing belief with a revolutionary concept. Black holes might not be inescapable voids after all. They could radiate energy, and astonishingly, might even completely vanish over time. This extraordinary theory, now referred to as Hawking radiation, reshaped the entire scientific view of black holes and posed deeply significant questions about the universe itself. To appreciate how Hawking arrived at this insight, we must explore the scientific landscape of the 20th century, a world dominated by two major yet discordant theories: Einstein's general relativity and quantum physics. Einstein's theory of relativity illustrates how mass distorts the fabric of space-time, generating gravitational effects. In contrast, quantum theory focuses on the peculiar and unpredictable behavior of particles at the tiniest scales. But black holes create a conundrum. They exist where gravity is so immense that quantum-level interactions become crucial, placing both theories in conflict. In the early 1970s, while at Cambridge University, the young Hawking began analyzing black hole behavior through the lens of both general relativity and quantum mechanics. Traditionally, black holes were thought to only accumulate matter and energy, growing larger while remaining inert. But quantum theory hinted at more exotic activity occurring near the event horizon, the invisible boundary where nothing, not even light, can escape the black hole's pull. To formulate his theory, Hawking dove into the strange, often paradoxical nature of quantum mechanics, especially the phenomenon of quantum fluctuations. According to quantum theory, what we call empty space isn't truly void. Instead, it constantly churns with spontaneous activity, where virtual particle-antiparticle pairs briefly form and almost instantly cancel each other out, leaving no lasting trace. However, Hawking proposed a radical twist. If such a pair appeared near the event horizon, one particle might fall into the black hole while its twin escaped. If this happened, the escaping particle would become visible to an outside observer, appearing as emitted radiation. This outbound energy came to be known as Hawking radiation. Hawking deduced that the continued escape of such radiation would gradually drain energy from the black hole. And since energy and mass are fundamentally linked thanks to Einstein's famous equation, equal 2 E equal mc, 2, the black hole would slowly lose mass, an effect termed black hole evaporation. If this process continued long enough, the black hole might completely dissipate, vanishing in a final outburst of energy. But the implications went even deeper. Hawking's theory didn't just alter black hole physics, it also sparked intense debates about one of the most sacred principles of quantum mechanics: the preservation of information. According to quantum theory, information about any physical system state is never truly lost. It might change form, but it should always be traceable. However, if black holes could emit radiation and eventually disappear, what would happen to the information about all the matter that once fell inside them? This dilemma became known as the information paradox. If information is lost forever inside black holes, it would violate quantum mechanics. If it survives somehow, then there must be a deeper mechanism we've yet to uncover. Physicists have been wrestling with this paradox for decades, and it continues to drive efforts to unify general relativity and quantum mechanics into a single, coherent theory. To visualize this, imagine a thriving city with a high-tech recycling facility where nothing is ever allowed to leak out. For years, everyone believed that anything that entered this plant was completely destroyed. Then, a scientist uncovers something strange. Under specific circumstances, tiny fragments of waste start escaping from the edges. And as more fragments escape, the plant itself begins shrinking until, one day, it vanishes entirely. Hawking's theory of radiation from black holes catapulted him into global scientific fame. His ideas opened a window into the quantum nature of gravity and offered a path toward understanding how the universe's most extreme forces interplay. Echoes of the early universe. The tale of primordial microwave radiation. As the universe grew and expanded over billions of years, the wavelengths of these ancient photons stretched, drifting into the microwave band of the electromagnetic spectrum. This redshifted light is what we detect today as cosmic microwave background radiation. Fast forward to the early 1960s, Arno Penzias and Robert Wilson, two radio astronomers at Bell Labs in New Jersey were testing a large horn-shaped antenna meant to detect faint signals for satellite communication. Instead of clean data, their equipment registered a puzzling background noise, a low, steady hum that seemed to come equally from every part of the sky. They meticulously inspected their instruments, suspecting possible faults or interference from the nearby city. They even removed pigeon droppings from the antenna, thinking that might be the source. Yet, the strange noise remained, consistent no matter the time of day, season, or antenna orientation. Their mystery noise found context when they contacted Robert Dick's group at Princeton University. Dick and his team had been working on verifying the exact prediction made by Gamo's team decades earlier, the residual radiation from the Big Bang. When Penzias and Wilson described what their antenna was detecting, Dick quickly recognized the immense importance of the signal and famously remarked, "Well, boys, we've been scooped." What Penzias and Wilson had detected aligned perfectly with the predicted leftover radiation from the universe's birth, cooled and stretched into the microwave range by billions of years of expansion. This momentous observation offered the first definitive evidence in support of the Big Bang theory. After this landmark discovery, scientists were eager to investigate the CMB more thoroughly. In the 1990s, NASA launched the COBE Cosmic Background Explorer satellite to study it with improved accuracy. COBE not only confirmed Penzias and Wilson's results, but also revealed tiny variations in the CMB's temperature, subtle differences that reflected slight density fluctuations in the early universe. These small variations were essentially the initial seeds that would later grow into galaxies, stars, and planetary systems. Even more advanced missions followed. The Wilkinson Microwave Anisotropy Probe WMAP and the Planck satellite built upon COBE's work, delivering incredibly detailed maps of the CMB. Thanks to these high-resolution observations, cosmologists could now calculate the universe's age, its composition, and even its geometric shape with astonishing precision. Think of standing in a canyon and shouting, then hearing your voice echo back after a delay. The CMB is the universe's ancient echo, a quiet, omnipresent murmur that holds critical information about our origins. Like an echo reflects a sound, the CMB reflects the state of the early universe, its energy stretched thin by time and space. In recognition of their groundbreaking, serendipitous find, Penzias and Wilson were awarded the Nobel Prize in Physics in 1978, cementing their accidental revelation as one of the 20th century's greatest scientific feats. Even now, research into the CMB continues to unveil secrets about dark matter, dark energy, and the universe's hidden architecture. What was once dismissed as an unexplained background hiss in a radio telescope has now become a foundational piece of cosmological science, a silent messenger from the birth of time itself. The bizarre bond of quantum interconnection. Though it might sound otherworldly, quantum entanglement is among the most rigorously tested and fascinating principles in the realm of quantum physics. It's a concept that defies our conventional grasp of space, time, and even the essence of existence. The foundations of this phenomenon were laid in the early decades of the 20th century, when quantum theory was still in its formative phase. To them, this eerie, instant interaction hinted at a problem within quantum theory itself. They proposed the idea to illustrate its incompleteness, theorizing that undiscovered, hidden variables might explain particle behavior in a more familiar, classical fashion. Then came the 1960s, when Irish physicist John Bell rose to the challenge Einstein posed. Bell formulated what is now known as Bell's theorem, a mathematical structure that allowed scientists to pit quantum theory against the hidden variable hypothesis through experimental testing. His work predicted that if quantum theory were accurate, entangled particles would exhibit correlations in behavior that no classical model could account for. In the decades that followed, particularly during the 1980s, numerous experiments put Bell's predictions to the test. Among the most notable were those conducted by Alain Aspect, a French physicist. Time and again, these experiments supported quantum theory's predictions. Entangled particles responded to each other as if linked by an invisible, instantaneous thread, regardless of the distance separating them. These astonishing results upended classical logic and confirmed entanglement as a genuine and fundamental feature of quantum physics. Quantum entanglement describes a situation where two or more particles become so deeply connected that the condition of one affects the other directly, even when they are separated by great distances. If one of these particles is measured, the state of the other is instantly known, no matter how far apart they are, even on opposite sides of the cosmos. To visualize this, think of flipping two coins that are somehow quantum entangled. Normally, you'd expect unrelated outcomes. Maybe one lands on heads and the other on tails. But if the coins are entangled, flipping and observing one coin causes the other to immediately reveal the opposite result. It's as though the coins are coordinating their responses across any distance, even if one is nearby and the other is on a distant star. In quantum terms, particles like electrons or photons can become entangled, sharing a combined quantum state. The measurement of one's properties, say, its polarization, immediately determines the other's, aligning it in a complementary way, no matter the physical distance between them. This defies the tenets of classical physics, particularly Einstein's theory of relativity, which asserts that no signal or influence can move faster than light. Yet, in the world of entanglement, the effect appears to happen with no delay. It suggests that space itself may not be as real or absolute as we perceive. Perhaps, at a fundamental level, all things are connected beyond the familiar notions of locality and separation. Though this concept is mind-bending, entanglement is far more than just a strange theoretical idea. It has powerful, practical uses, especially in the fast-developing area of quantum computing. Unlike classical binary bits, which can be either 0 or 1, quantum bits or qubits can exist as 0, 1, or a combination of both simultaneously due to a phenomenon called superposition. When entangled, qubits can interact in highly complex ways, making it possible for quantum computers to solve certain problems vastly faster than traditional machines. Another remarkable application is found in quantum cryptography, which leverages entanglement to create ultra-secure communication systems. Any attempt to intercept or tamper with the entangled particles used in communication would instantly disrupt their connection, alerting users to the intrusion. This could revolutionize digital privacy and usher in an era of virtually unbreakable encryption. Entanglement is also central to quantum teleportation research. While this doesn't involve physically moving objects like in sci-fi movies, it does allow for the instant transfer of quantum information from one location to another through entangled particles. This could drastically transform how we handle data and communication across long distances. Ultimately, quantum entanglement forces us to rethink the very fabric of reality. It stirs deep philosophical questions. What is space? What is time? Are all things somehow intertwined beneath the surface? Could there exist a hidden layer of reality that binds everything together? Some scientists and philosophers believe entanglement may offer clues to a deeper, more fundamental framework of existence, one that lies beyond what we can observe directly. The mechanism behind this interconnection remains unknown. Is there some secret force linking entangled particles? Or is our understanding of space and separation inherently flawed? In grappling with these mysteries, quantum entanglement urges us to keep questioning and expanding the limits of our understanding. This strange and beautiful feature of the quantum world, made famous through the efforts of Einstein, Podolsky, Rosen, Bell, and many experimental pioneers, teaches us that the universe doesn't always play by the rules we're used to. It points toward a cosmos where distant particles can influence one another instantaneously, as if whispering across the void. Through the lens of entanglement, we begin to glimpse a universe that's more intricately connected than we ever imagined. a place where beneath the surface, hidden patterns and unseen links may weave the fabric of all things. As we explore this fascinating territory, one thing becomes clear. Reality is far more complex and mysterious than it seems. And it all may trace back to the moment of creation itself, the Big Bang. Origins of the universe. The story behind cosmic expansion. Imagine turning back time on the universe's entire history, like rewinding a movie. Galaxies reverse their course, stars shrink inward, and vast clouds of gas and dust fold into dense clumps. This reverse journey reveals a cosmos that once existed as an inconceivably tiny, scorching, and tightly packed point. This idea, what we now call the Big Bang Theory, is the leading scientific model explaining how the universe began and transformed over time. But this theory didn't appear instantly. It emerged after decades of intense debate, mounting scientific proof, and unexpected breakthroughs. The origins of the Big Bang concept trace back to Albert Einstein in the early 1900s. In 1915, Einstein unveiled his general theory of relativity, revolutionizing how we understand gravity on a grand scale. His theory showed that enormous objects distort the fabric of space and time around them. However, when Einstein extended his equations to encompass the universe as a whole, he encountered a conundrum. The math indicated either expansion or contraction, contradicting the then dominant belief that the cosmos was fixed and unchanging. To reconcile his equations with this steady-state model, Einstein added a cosmological constant, a tweak that would allow for a static universe. At the same time, Belgian priest and mathematician Georges Lemaître noticed something intriguing in Einstein's equations. In 1927, he proposed a daring idea. The universe was not motionless, but expanding. Lemaître theorized that if we reversed this expansion, everything would converge to a singular starting point, what he called the primeval atom. From this origin, the universe burst into existence. At first, this notion seemed far-fetched, even Einstein rejected it. But things changed in the late 1920s when American astronomer Edwin Hubble delivered stunning observational evidence. Using the advanced telescopes at Mount Wilson Observatory, Hubble observed faraway galaxies and noticed something remarkable. They were all receding from Earth. Even more surprising, galaxies farther away were moving faster. This discovery, now known as Hubble's law, confirmed that the universe is expanding. Galaxies weren't stationary, they were drifting apart, as if the universe itself was stretching. Hubble's findings gave solid support to the notion of a dynamic, expanding cosmos. Still, the scientific community remained split. Many clung to the idea of a steady, unchanging universe. One of the most powerful confirmations of the Big Bang came by accident in the 1960s. Physicists Arno Penzias and Robert Wilson, working at Bell Labs in New Jersey, were testing a giant antenna designed for satellite communication. But their experiments were being disturbed by a persistent, unexplained hiss of static that seemed to come from every direction. They tried everything, even removing bird droppings from the antenna, to eliminate the noise. But the hiss didn't go away. As it turned out, Penzias and Wilson had unknowingly detected something revolutionary: the cosmic microwave background CMB radiation. This faint, uniform glow, now known as the afterglow of the Big Bang, was the lingering heat from the universe's explosive birth. The CMB offers a direct glimpse into the universe around 380,000 years after its origin, when it had cooled enough for atoms to form and light to travel freely through space. This finding was historic. It served as a fossil imprint of the early cosmos, a smoking gun that confirmed the Big Bang model. According to the Big Bang theory, around 13.8 billion years ago, the universe originated as an intensely hot and dense point, often referred to as a singularity. For reasons still unclear, this singularity began to expand rapidly, launching the process of cosmic development. In the immediate aftermath, the universe was a chaotic soup of particles, protons, neutrons, electrons, far too energetic to form atoms. As expansion continued and temperatures dropped, these particles merged naturally, giving rise to hydrogen and helium, the first atoms. In the next several 100 million years, minor differences in matter density caused gas clouds to collapse under gravity, forming the first stars and galaxies. Over time, stars lived and died, galaxies collided and evolved, and the complex structure of today's universe began to take shape. To visualize an expanding universe, imagine a balloon dotted with ink spots. Each represents a galaxy. As the balloon inflates, the surface stretches, and the dots move apart. Similarly, galaxies are not flying through space, but are moving apart because space itself is growing. The Big Bang Theory forms the backbone of modern cosmology, offering a coherent framework for how the universe came to be and how it has evolved. Still, many profound questions remain unanswered. Scientists still don't fully understand what caused the Big Bang. The theory doesn't clarify what existed before this event, or if before even makes sense in this context. Moreover, discoveries in the late 20th and early 21st centuries have exposed further mysteries. Observations suggest that dark matter, which doesn't emit or interact with light, helps hold galaxies together. Meanwhile, dark energy seems to be accelerating the universe's expansion. These two components, though invisible, account for the majority of the universe's content, yet their true nature remains elusive. This opens the door to the possibility of a deeper, more all-encompassing theory of the cosmos. The Big Bang Theory stands as one of science's greatest achievements. Through the observation of galactic motion and the detection of cosmic background radiation, researchers have assembled a narrative that connects us to a distant, fiery origin. It reshapes the universe from a passive stage into an active, changing entity with a beginning, a progression, and possibly an ultimate conclusion. And while the Big Bang Theory answers some of humanity's grandest questions, it also reveals new ones, new mysteries, and new horizons to explore as we strive to understand the full story of our cosmic birth.